In the next few examples, we want to look at finding the y-intercept of a given exponential function and then talk about its end behavior. In example 1, we have the function 8 times 5 to the 9 times x power. So keep in mind that 5 is being raised to the power 9 times x. All of that is in our exponent. What we want to do in part A is find the y-intercept, meaning we want to find a point of the form 0, comma y. So our x value has to be 0. That means we'll evaluate g of 0. To get 8 times 5 to the 9 times 0 power, which will be 8 times 5 to the 0 power. Anything to the 0 power is just 1, so we'll end up with 8 times 1, or 8, as our y-coordinate. Our y-intercept then occurs at the point 0, comma 8. And then if we notice, this value is exactly the same as the initial value in our original function. As long as we have a function of this form, that will always be the case. The initial value will give us the y-coordinate of our y-intercept. That can change if we have a more complicated function. So for instance, if there was any term added or subtracted in the exponent, or if we were adding a value on here, say plus 4. But if we have something of this form, that initial value will always be the same thing as our y-intercept. Then we want to identify the end behavior of this function in part B. We already talked about the general form, what the graph of an exponential function looks like. In this case, because our value c, or that growth rate of 9, is greater than 0, we know that our function is increasing as x gets larger. So as x approaches infinity, our function value for g will be approaching positive infinity. And as x approaches negative infinity, the function value g will be approaching 0, that horizontal asymptote on the left end. In example 2, we want to repeat this process, but notice that what we have a little bit different here is a negative value for that growth rate. So negative 8 is less than 0, so this function would be modeling exponential decay. To find our y-intercept, again what we'll do is set x equal to 0, which will give us 3 times 9 to the 0 power, because negative 8 times 0 will just be 0, or 3. Again, that y-coordinate matches up with our initial value. And our y-intercept will be the point 0, 3. Talking about the end behavior, since this is an example of exponential decay, since that growth rate is negative, that means that our function will be decreasing as x gets larger. So in this case, as x approaches infinity, our function value will be approaching 0. That horizontal asymptote is now on the right end of the graph. And as x approaches negative infinity, the function will be approaching positive infinity. As x gets smaller, the function value is increasing. In example 3, now we have a base e exponential function. Keep in mind that's just a number, a specific mathematical constant. So we have a number being raised to a variable power. In order to find the y-intercept, since we have the function of this same form, a times some base to the c times x power, our y-intercept will be 0, comma 10, the same thing as that initial value in our exponential function. And since again our growth rate is negative, we have a case of exponential decay, meaning that as x approaches infinity, the function value will be headed to 0, and as x approaches negative infinity, the function value will be headed off to positive infinity.